对，然后就开始好了。Okay, so firstly, let me briefly introduce this AI for All Institute. It's not officially launched yet, but we are trying to build an AI community of all, by all, and for all. Okay, so everybody knows that this year the Nobel Prize in Physics and Chemistry was given to people in AI. So I think that's big news for all the people in AI, and AI will be more influential. And inspired by this, and also by the Nobel Prize in Economics, we build this AI for All Institute, and we want to make it inclusive, so for its bias property. And this is the Telegram. Welcome to join it. So today we have actually two talks. The first one by Charlie Snail, and second one this one by Yu Gu. And I briefly mentioned this. There's a magicu.me. It's a platform for collaboration and communication. We hope to make this the platform for our AI community, but it's kind of a beta test stage. So welcome to test it. So let me briefly introduce Yu Gu. He's a PhD student from Ohio State University. Let me see. Actually, let me see. Yeah, sorry. Actually, he is the recipient of several ACL and cooling, right? The best paper for those two conferences.
Outstanding paper. Sorry.
Okay, outstanding paper. Okay, that's also very good. That's very difficult. Yeah, so actually, people can always check the website, those things. So without further ado, let's welcome Yu for the talk. Okay, how to do that? Let me see. Yeah, can you share it or your screen or not? Let me see.
Yeah, let me try.
Let me make you a co-host. Okay.
Can you see my screen now?
Not yet. Oh, maybe I should stop my.
I think I already shared my screen.
Maybe can you do that again?
I can see it.
Can you see it?
Oh, okay. Somebody can see it.
Oh, you cannot see it? Maybe I can retry. Let me retry.
Maybe you stop and start again.
Yeah,
Okay, that's great. Yeah.
It works now?
Yeah, that's
Okay,
great.
cool. Okay, cool. Thanks, Dr. Lee, for the nice introduction. And I'm very excited to share some of my thoughts on language agents. And so my goal today is to kind of like convince you that language agents are not just a fleeting hype, but a profound area worthy long-term commitment. But yeah, probably I cannot like convince everyone, but that's my hope. So let's see like how I can do it. And specifically in my talk, I will try to compare language agents with some classic AI agents, for example, like the classic rule-based agents or maybe RL agents in a kind of like maybe a more systematic way, maybe an apple-to-apple manner. And I will also try to lay out several milestones in my mind for studying generalist agents powered by natural language. So without any further ado, let's just get started. So you probably have heard about AI agents very frequently these days. So this is a slide I've been using for over like 1 year. So sorry, so all of them are kind of like popular libraries from 2023 on like language agents or AI agents in general, like specifically LLM-based agents. So for example, like AutoGPT or LangChain. And after 1 year So the popularity continues to rise instead of fading away. For example, you might like see some news on platforms like Google News or maybe VentureBeat regarding AI agent every several hours. And almost like every several days, you can see maybe a kind of like new investment going to a new agent startup or something like that. And also similarly in academia, it's just some several like screenshots from this year's iClear submission. All of them are about like agent or yeah, it's just to show you that the term agent is actually being quite popular these days. But the term agent itself is not, it's really not something new, right? And I know like many people, they actually hate the way that some LLM people reinvent the term agent. And trust me, I believe I'm not one of them. And I want to stay more faithful to the literature of AI agent. So let's start with the like classic definition of agent. So this is a definition from the classic AI textbook, AI Modern Approach by Russell and Novick. So the definition is actually quite broad and intuitive. So it basically says that anything can perceive the environment and take actions within the environment can be called an agent. Right, this is a very kind of like broad description. And we can also have a more modular definition of agent. So basically, I think agent has three components: environment, goal, and planning. So for environment, it basically means like anything that can provide feedback, including a physical environment. For example, if you have a robot like operating within physical in your maybe in your house, then the environment is basically the like the physical world, or maybe like the environment can also be digital world, right? Your agent can be maybe sometimes it can play video games, or maybe it can help you to like do some jobs maybe using Office or something like that. So in that case, the digital world will become the environment. And also even humans can be the environment to the agent, because humans can also provide feedback to the AI model, right? For example, if the AI model is playing chess or playing Go against a human, then the human is also part of the environment. Well, regarding the goal, basically anything you can imagine, like humans can achieve. For example, like to clean a room, to win a game, or to answer a question, something like that. And regarding planning, it basically means that because sometimes a goal can be hard to achieve, you cannot just achieve the goal by taking one action. Instead, you need to do some multi-step decision making, which might involve some policy-based method. It's very common for like the RL literature, and also for some maybe early works like expert systems, people adopt the search-based method. But for some more complex tasks, people may use hybrid approach, which combine both policy-based method and search-based method. So a classic example is AlphaGo, right? It uses both policy model and also value function plus MCTS to guide the search process. So we can look at some examples of classic AI agents. The first example is also from the book by Russell, the modern AI modern approach. So this is actually a minimal example to show the concept of AI agent. So here you have an environment, basically two rooms, and also each room may optionally has some dust in it. And the goal of the agent is to keep the room clean. And to achieve the goal, the agent may need to decide whether to go to the next room or clean the current room. So this is a very simple example, and the policy can simply be achieved using some handcrafted rules. And also the second example, so this is a agent playing car reading game, and the goal is to decide whether to turn left or turn right in order to move along the track without going off the road. And also we have talked about AlphaGo, right? So this is kind of like an agent playing against a human opponent, and the environment involves both the board and also the human opponent. And the goal is to beat the human opponent. So what's wrong with these agents? So they are all kind of like classic examples. So what's wrong with them, and what's the gap between them and our goal of like generalist agents? So in short, they are all specialist agents that focus on a very specific goal. For example, it's either like clean a room or win a reason game or beat opponent in Go. It's quite specific, right? You don't have the flexibility to kind of like change your goal or to specify different goal to your agent. And the natural question is, what's the best way to specify general goals? I guess probably no one will have a like different answer to this. Probably, right? So as human beings, we have like a most powerful tool to specify or to express infinite meanings using natural language because of the compositionality nature of natural language, right? And also, I want to mention that language can do much more than merely specifying goals. And this leads to the main content of this talk. I want to lay out 3 stages towards generalist agents powered by natural language. And the first stage is very clear, which we have briefly touched. So we want to have agents that can handle and now specify goals. So in this way, we allow the agent to handle more diverse goals, and we also allow the human users to specify the goals in a more flexible way. But for stage 2, the agents should also be able to like think in natural language to make better decisions, in addition to just respond to different and now specified goals. And this is actually the defining nature of what we call language agents. And we will see more examples later. And regarding the third stage, it's more of like a long-term thing. And existing research on this stage is still quite preliminary, but I will still try to cover some like background or maybe some of my vision into this stage. But mostly my talk will be revolved around the first 2 stages. So to study the language-powered agents, we need to first have good language-driven tasks to serve as our testbed, right? If there's no good testbed for the goal, we will not be able to kind of like move along this journey. And so if we look at existing natural language processing tasks, so I'm from the natural language processing community, and also for the like language-driven tasks, it's probably the most natural thing to do is to find a task from the NLP community, right? And remember that there are several key components that define an agent. We need to have an environment, and also we want the tasks to involve planning. So we can have a kind of like a hierarchy of existing NLP tasks in terms of whether they involve an external environment or whether they require the model to do multi-step planning. So for the first level, it's basically the most kind of like preliminary NLP tasks that involve no environment and no planning. For example, like a lot of like sentence classification tasks like sentiment analysis, natural language inference, things like that. So some chat, some message. Do I need to respond? Wait, sorry. So for the level 2 tasks, they basically tasks that involve no environment, but with certain form of planning. For example, like machine learning or text summarization. Because to generate the final output, the final sentence, you need to do some like planning in terms of like structuring the sentences. Also for level 3, this task involve grounding to an environment, but only require offline planning. So here we will briefly explain a bit on the term offline planning. So by offline planning, it means that the model can directly compute a plan without interacting with the environment. And this is because the environment itself is just too simple. You can directly input the environment to the agent. So the agent knows everything about the environment. As a result, it does not need to interact with the environment online to gather new information. And this is probably not something we want, right? Because in realistic setups for agent tasks, the environment can always be very complex. And the agent typically only has maybe partial knowledge about it. So what we want is tasks that involve not only just grounding to an external environment, but also online planning. And this is our goal. So what's going to be the good task, like good level 4 task for us to study language-powered agents? So like at the time of, in era of BERT or T5, the best thing we can do is probably KBQA or knowledge-based question answering. And here I will briefly explain why KBQA might be a good test bed as a good example for the level 4 task. So here is a small example of a knowledge base with nodes representing entities in our world, and also ages representing the relations between entities. So note that this is only a toy example just for the ease of presentation, but in reality, knowledge bases or knowledge graphs can be very, very massive. For example, like Freebase may have like billions of ages, and Google knowledge graph may have maybe trillions of ages, something like that. And the task of KBQA is to navigate along the KB to find the target entity which answers a given question. So for example, in this question, it asks about who painted the painting that James likes. So the first step is we need to know where to start. And because the question mentioned James, so we start from the entity James. And then we navigate the KB to find the target answer step by step. So the first step to do is to find the painting that James likes. And then we find who actually painted that painting. So the answer is Da Vinci. So why this is this recalls online planning? Because one thing we can notice that is in a like knowledge base, at each step, the action space is actually different. For example, for the first step, when the agent determines to go along the likes relation, there are actually also other 5 candidate relations to navigate. So in the first step, there are 6 legal actions in its action space. While for the second step, there are only 3 relations or 3 ages connected to Mona Lisa. So as a result, the action space for the second step is different from the first step. And if the agent wants to know like which actions are legal for each step, the only thing it can do is to actively interact with the KB to determine it. So as a result, KBQA might be a good test bed for language-driven tasks that require both grounding to external environment and also online planning, requires actively interacting with the environment. However, KBQA benchmarks in 2020 usually operate with an IAD assumption. So by IAD assumption, I mean the navigation pattern during training, in training set and test set are almost the same. As a result, the model can just memorize the navigation patterns in the training set without actually interacting with the environment. So as a result, this makes online planning unnecessary for these benchmarks. To address this issue, we propose a new benchmark that focus on non-IAD generalization. So in this way, the model cannot just simply rely on memorizing the patterns in the training set. Instead, it actually needs to interact with the KB to understand the current context and to determine the next step, the legal actions for the current step. So one thing I want to briefly mention is that, so we mentioned that the task for KBQA is to find a way to navigate over the KB to find the target answer. But the actual output of the task is actually a problem which defines how we navigate the KB. So this is just kind of like a concise representation of the navigation pattern. You don't need to pay attention to the detail here, just to have some general sense about the background here. And a question is, why don't we just resplit existing data sets to kind of like ensure non-ID generalization? And the answer is very simple, because existing data sets, they only have very limited coverage of relations and classes. But our data set covers more relations and more classes. So we can more easily control our data split, and meanwhile we can have like a large scale set for both training and test. And the thing I think we need to pay attention to is just the number of relations classes here. It basically kind of like shows you a general sense about the complexity of the action space, because when navigating the knowledge base, you need to determine like which relation to select for each step. And our first solution to this problem is called ArcAnQA. So this is an encoder-decoder solution to kind of like take in the natural language question as input and output a problem that we just described before. And this is kind of like something very natural, right? Because like language models or encoder decoders, or maybe just decoder models, like at that time when we released the data sets, kind of like a common practice for almost all NLP tasks. Well, one core issue for encoder decoder language models to handle the KBQA task is that they're typically trained for free-form text generation with a fixed vocabulary at each step. Well, for our KBQA task, remember, at each step, the legal actions are different. So this is kind of like a misalignment here, right? Because for most other tasks like machine translation, you just keep a kind of universal vocabulary for every decoding step. And our solution, the core idea of our solution is also very simple. So we just dynamically mask the vocabulary based on the KB context at each decoding step. And then we use beam search to find the most probable actions sequence. And the idea is that to determine the vocabulary, the admissible vocabulary at each step, we need to incorporate the information from the KB context. Just like the previous example, how we determine the legal action for each step by looking at the surrounding relations of the current entity. And this is so this is kind of like a work from 2 or 3 years ago. Some of the idea might be outdated, but the general sense of kind of like constraint decoding or to dynamically determine action space is still something critical for current agent research. And this is just a high-level overview of the framework. You can see, like at each step, we need to determine the admissible tokens based on the current context in the KB. And also, we need to encode this kind of admissible tokens together with the question to generate a more accurate representation. And to actually implement the dynamic vocabulary masking, we need to handcraft a set of rules. For example, you don't actually need to pay attention to understand this, because I also don't remember all these rules fully. So the key idea is just we need to handcraft some rules. The rules is basically something like based on the tokens of the previous step, or maybe previous 2 steps, what's the admissible token for the next step, something like that. Totally rule-based for the vocabulary masking. And this is a high-level idea. However, after doing this, we find that the crafting rules for dynamic vocabulary masking is extremely hard. As I just mentioned, for crafting the rules I just showed, I actually kind of like coded more than maybe 1,000 lines of Python code. And also autoregressive decoding itself is inherently short-sighted. So to address this, we present another solution. So what about, like, let's just let the language model discriminate instead of like generate the problem by itself. And the intuition is that we can actually construct or enumerate complex problems incrementally from the KB. For example, in step one, we can actually enumerate several problems from its based on its context. For example, this is a problem, so we can directly enumerate, right, based on the neighboring relation of gems. For such kind of problems, we can actually enumerate 6 of them, and we just ask the language model to determine which one is the best, and assume the model can actually score the right problem as the highest one. Then we can expand the program into a more complex problem at the next step, right? So this is just some basic intuition that you can directly enumerate the problem from the environment, from the KB, and you ask the language model to score the problem instead of generating this problem. And this is also a high-level overview of the paradigm. And yeah, you still don't need to pay too much attention to the details. And the thing is that we find that this new method, the discrimination method, Pangu, is much better than the previous RCan method. And one thing, one interesting finding from this work is that because we want to know why like the discrimination model actually performs much better than the previous decoding-based model. So in particular, we find out that the discrimination model is particularly strong in the non-ID setting. So what we do is that we actually look into the kind of like the distribution of scores for KB navigation patterns in the test set that are seen during training and unseen during training. And surprisingly, we find that for RCan, for patterns on the KB that the model actually is seeing during in the training set, RCan assigns extremely high confidence to it. It's a very skewed distribution. While for the unseen programs, the distribution is much different. While for the Pangu, for the discrimination model, the distribution for seen and unseen patterns, they are almost the same. And this might explain the robustness of Pangu in the or discrimination model in the non-ID generalization setting. And interesting, this is also related to the kind of like discriminator generator gap people have been talking about these days. And this is one of the reasons behind is why RLHF can work. But yeah, but maybe not entirely the reason, but probably one of the reasons. So however, yeah, you probably feel a bit bored because these two works, they still feel somewhat reminiscent of the kind of like pre-LLM era. They're quite different from like how people approach the problems these days. So we are ready for an upgrade. So in this diagram, and actually we can just forget about what we have been talking about. So in this diagram, I show the performance of different methods still on a KBQA dataset, but this is a particularly challenging subset that I intentionally created to challenge the large language models. We can see that when using GPT-4, even Pangu can only achieve like 27% accuracy or F1. But for RCan we cannot do that because RCan requires us to hack the decoder of the model. Well, here is another model that easily doubles the performance of Pangu. And this is the one that I will kind of like briefly talk about in the next chapter. So this work is a more recent work just published at the EMLP. And it also marks a shift from stage 1 to stage 2. So now we can finally enter stage 1 agent, which can use its natural language as a welcome thought, not just to understand like the NL specified goals, but now the agent can actually use language to guide its thinking process or maybe decision-making process. So yeah, as I mentioned, the magic behind the stage 2 agent is just language as a welcome thought. So this is basically the intuition behind chain of thought, COT. Probably everyone is super familiar with that. So for COT, instead of directly asking the model to output an answer, COT prompts the model to first generate a rationale before it generates an answer. And when generating the answer, it can actually condition on the previously generated rationale. And as a result, it can generate the answer more accurately. So this is a kind of like the intuition behind the COT, because the rationale provides more context for the answer generation. And as a result, the generated answer can just be more accurate. And also similarly for React, which kind of interleaves reasoning and acting. So it's very similar to COT. So basically for your agent actually step, before it generates, it decides on an action, it will first generate a thought or a rationale in natural language. For example, like before the agent decides to take the action to search for an Apple remote, they will first generate the rationale or reason for why it wants to take this action. And as a result, the action generation can be more accurate. So both of these two examples show the high level intuition, the same intuition, that using language as a local of thought. And this is a critical nature for language agents or the stage 2 agents. And we can similarly do the same thing for our KBQA task. And the key lies in create a set of tools for our agent or for the LLM to use based on its own thoughts. And there are just some example tools. For example, we can provide the tool so the language agent or the LLM can just call this tool to get relations, the neighboring relations of an entity. You don't need to pay attention to detail, just have a general sense. And this is a concrete example of how the model that call these tools to accomplish a KBQA task. It's very similar to the React setup. And it's actually kind of like a common practice, common standard these days. So far we have been focusing on the KBQA task, but probably it's not the most interesting thing that people like care about in the era of like large language models. So I mentioned before that because in the era of BERT or T5, KBQA is probably like the most ideal task we can handle. But now we have large language models. We can do something maybe fancier. So there's some limitations of KBQA. The first thing is that the sensory inputs from KBs are much less complex than observations in real-world environments, because the inputs from the KB are just relations or just ages, right? And the second, the exchange with the KB is very cheap. So it's a purely kind of like digital environment that you can query it just like a database. There are many mature commercial query engines that can maybe query the KB over maybe 1,000 times in 1 second. And also because KBQA is mostly about querying, and there's no state changing action. As a result, backtracking or parallel search is very trivial over the KB. But in realistic environments, both backtracking and parallel search can be very difficult or just infeasible at all. And this makes search a very different story for realistic like agent tasks. And also the planning part is very straightforward, because in KBQA, is like everything you need is already kind of like included in your question. For example, if you ask like who painted the painting that James likes, you can directly tell that this is kind of like two half question just based on the question or the goal itself, right? But this is not desirable for realistic tasks. For example, in reality, the goal can be more high level. For example, if you ask the agent to make a pizza for you, then the agent need to figure out like the low level steps all by itself. It's not like explicitly mentioned in your goal. So this is similar to the comparison between declarative programming, like SQL or maybe Sparkle, versus imperative programming like C++ or Java. So with large language models, we can look into something fancier. So this is a new environment web agents that we cannot handle in the era of BERT or T5. But now with large language model, we can allow the model, the agent to perceive this kind of like multi-model sensory input. So this is some, these are 9 examples from the Mind2Web dataset released by us. So basically for each example, you can see on the top of it is natural language specified goal, for example, to book a flight on the website, or maybe to kind of like yeah, like to order like Apple Care on Verizon website. So, and the agent needs to decide what actions to do on the website step by step to achieve the goal. So you can see the agent just autonomously click all these different buttons and fill in different forms by itself. And for this new environment, different from the KBQA setup. So now we have more complex inputs, and also the interactions with the environment is much more costly, right? Because you cannot just like you cannot just create maybe 100 instances of like the interaction with the websites in parallel. So this is going to be too costly because of the, for example, like the network traffic or like the latency in network communication. And also the planning is not as trivial as KBQA, because as I mentioned here, you only specify a high level goal, like find one-way flights from New York to Toronto. But how do you do that step by step? How do you convert that into low-level actions on the website? This is something that the agent need to figure it out by itself. So that involves more like challenging planning. And this is a more concrete example using the CACT framework, also released from our group. So we can look at the simple tasks that try to compare two different models, iPhone 15 Pro Max and iPhone 13 Pro Max on the official website of apple.com. And on the left side is the action that the model is actually doing. But on the right side is kind of like the thinking process of the model. Remember, like the key feature of the stage 2 agents is that it can rely on the language as a welcome thought, just as we show in the example of COT or React. So let's just look at this example. So you can see at each step, the model receives some input from the environment, and then it generates a thought for its action, and then it converts action into a concrete execution environment. And finally, it can just achieve the goal. So there's another example, but we can just skip it. So the core challenge here lies in planning. As I mentioned before, like planning for web agents it's much more challenging than the previous examples we have seen in KBQA. And the question is, how do you do planning in such environments? So I think planning, there's a simple equation for planning in this kind of complex environments. So basically planning equals policy plus search. So for the policy part, so both the KBQA setting and also the web agent setting, we are currently mostly rely on things like React using large language models. The key difference lies in the search part. So in KBQA, so we heavily rely on things like BM search to find the most promising trajectory. This is very trivial because, as I mentioned, like in KBQA, there's no state changing action, no irreversible action, and also the exchange with the environment is very, very cheap. But this is different for real world environments like the web environment due to the costly exchange and also irreversible actions. For example, on your website, if you kind of like confirm a purchase, you cannot just go back to the previous state, right? And because of these kind of irreversible actions, you cannot easily do things like backtracking, which is kind of like key requirement for many search algorithms. So based on this, how can we still like try to improve the planning in web agents. So web agents is kind of like a good test bed for more realistic environments. So here, the big question is that, can we like try to improve planning in more realistic environments, given this kind of challenging exchange with environment and also the kind of irreversible actions? So the most straightforward way to do it is just the so-called greedy setting or maybe reactive setting. This is also something we have seen in our previous demo using CACT. So basically, at each step, the model only chooses the most promising action based on the current step and execute it without any systematic exploration. So this is fast and easy to implement, but it's kind of like very short-sighted, and intuitive is going to be like definitely going to be very going to be suboptimal because there's no search at all, right? It's basically purely policy based. And the second way is that you can probably do something like tree search with real interactions. We just directly explore the environment. This can allows us to have some systematic exploration, but there are some issues involving irreversible actions, as I mentioned before, and also there are some safety issues, and also it's quite slow because you're interacting with the live website. With real interactions, there will be a lot of like latency in the communications. So a more promising solution might be model-based planning. So in this way, we do not need to actually explore the website, the search space with real interactions. Instead, we use a world model to simulate the outcome of different actions, and then we do the search process within the simulation space. So by doing this, we can be much faster than tree search method, and still it kind of like have the feature of systematic exploration compared with the reactive baseline. But the problem lies in how to get a world model, right? It's not kind of a trivial thing to learn a world model for something like the internet or for like diverse websites. This is also very different from maybe the world model in common environments that commonly seen in the RO setting, which typically feature some continuous transitions or continuous actions. But in websites, everything is totally discrete and also can be much more diverse. So getting the world model is very challenging here. And we actually have like a simple prototype for doing this. And the intuition is that your LLM may reasonably predict the outcome of an action. For example, like we test this on GPT-4o, like given the website, and we ask the model to predict what's going to be the outcome if we click on this image. And we find that a model can reasonably predict the outcome of this action. So it says that this is going to be a detailed product page of this men's flowers, casual aloha, Hawaiian shirt, summer short sleeve, something like that. So based on this intuition, we propose a simple solution, but this is kind of like a very early attempt to do kind of like model-based planning for web agent tasks. But as a kind of preliminary effort or a proof of concept, we show that if we just use GPT-4 as a world model to simulate the outcomes of different actions, we can actually easily get a boost by like 33% relative gain compared with the reactive baseline. Just super simple. But still, as I mentioned before, so this is kind of like a preliminary effort to a very difficult problem. And so for real world environments, so world model is the key because it allows you to kind of more effectively do search, and also related to the recent trend of discussion on scaling inference time compute, right? You need to have a way to do search more effectively, and world model might be the kind of like key answer here. And also, the intuition is still like we can leverage language as vehicle of thought for word modeling. So far we have like covered some representative works during my PhD in stage 1 agents and stage 2 agents. But still, there is a remaining question, like how do you go from stage 2 to stage 3? So basically, how do you use language also for learning? And regarding this point about like using language for learning, I want to first introduce some background on it. The background I want to mention is some findings from the development psychology community or maybe cognitive science research. And the claim is that language can shape the prior of human cognition. And this is a very interesting example from the psychology research. So it's actually an interesting human experiment. So in this experiment, so each participant is asked to classify a color wheel into either category A and category B. So at the beginning, the participant has no information about how to classify it. But each time, once it sees a new color wheel and it assigns a category to it, the system will notify the participant whether the classification is correct or not. The task is super simple. And they actually conduct 2 different experiments. So for the first group of experiment, there are 2 classes, which are based on more nameable colors. For example, for the 2 categories, the color just red, blue, and purple. And the way to actually the underlying rule to classify the patterns is actually just to look at the top right sector of the circle, right? So if the top right sector is blue, then it's classified as category A. If the top right sector is orange, then it's classified as category B. So the participant does not know this rule at the beginning, but once it sees more examples from different categories, it might be able to learn the rule. And the pattern is actually the same for the second experiment. But the only difference is that the color is still kind of only rely on the top right corner, top right sector to do the classification. But the color in the second group is hard to name, right? I actually don't know how to say them in English word for the 2 colors here. And an interesting finding is that even the 2 tasks, they have the same pattern. But for like the experiment with more nameable colors, people can easily get a much higher accuracy compared with the low nameability setting. And this is not just for colors, but also for shapes. So this is the same pattern as the previous task. You just do classification based on the top right sector. And in the first high nameability condition, the shape on the in the top right sector is probably maybe this is a tower and this is a swan or something. But for the second group, you really don't know what's the shape stand for. And the similar finding can also be obtained from this group of experiments. And the conclusions that nameable features make category learning easier. And this indicates that people rely on natural language concepts to do reasoning. And also, actually, there are many more evidence on this from psychology research. I won't talk about the details, but all of them, they point to the exact same conclusion that language shapes the prior of human cognition. So as a result, I'm really not a fan of description like the term like overfitting or vulnerability to adversary attacks, because these terms they do not reveal the essence of the problem. So what's the essence of the problem? In my mind, in my opinion, the essence of the problem, including like overfitting or vulnerability, they all stem from misalignment between human priors and inductive biases in machine learning. So people actually have leveraged this to do better image classification in machine learning. So this is a very interesting work from ICML 2020. So the idea is quite simple. So instead of asking the model to directly assign a label to a given image, instead they first ask a model to generate some intermediate features for some pre-specified concepts by human experts. And then the final label can be aggregated from the predicted features. For example, to identify the bird, the species of the bird in this image, the human expert will first specify some concepts like wing color, on the tail color, or kind of like beak length, something like that. An interesting finding is that they find that this kind of language-based features can lead to more robust performance. So in this experiment, they actually kind of like manipulate the background of two types of bird to create a spurious correlation between the background and the type of the bird. But actually, to do the task, you need to focus on the bird itself, right, not the background. And they find that in this setting, so they're kind of like concept-based or language-based features lead to much more robust performance. So the standard way is just kind of like vanilla CNN model without any intermediate feature, while the later three method are their method based on language features. You can see the error rate is much lower, and this shows the potential of like using language to shape the prior also for machine learning. But 4 years ago, like things are still quite limited in terms of like processing natural language. Well, now with large language models, we're now uniquely positioned to engage in language-based learning in a more advanced way compared to this kind of very preliminary effort that only rely on like human specified concepts. It's kind of like quite inflexible, right? So there has already been some early efforts on constructing external memory organized with natural language concepts. It's kind of like preliminary effort from stage 2 to stage 3. For example, this work is called HippoRag from our group. So basically it uses natural language to reason over maybe like a textual paragraph and then retrieve a large graph from the textual paragraph and save the large graph as an index or as like a part of the external memory. And also this is another work from CMU that it's try to construct the procedural knowledge by in the web agent scenario by interacting with the environment. So specifically, when interacting with the environment, the agent may find some common patterns, and then it can summarize the common patterns into some high-level description of the workflow. For example, something like if I want to find the flight from city A to city B, what kind of operations I need to do, something like that, some procedural knowledge. But as I mentioned, so this is still some very preliminary, very early efforts, and we definitely cannot just call them stage 3 agents or just call them like agents can learn using natural language. But I think this is a very promising direction because it kind of like connect learning and inference. Because in this setting, so learning basically equals inference plus memory, and probably you know that many people have been criticized the current paradigm machine learning, where the learning part and the inference part is totally disjointed. While in this setting, we might have a new opportunity to kind of unify learning and inference. So let's have a kind of brief summarization of language agents compared with rule-based agents or RL agents. And in this way, I want to just give you a kind of like more concrete idea of this new paradigm and what kind of like new opportunities you may unlock. So first, the goal space can be very different. So for language agents, we have like a new way to specify general goal. And also for conventional agents, the goal state may typically be like easily verifiable. For example, if you are playing games, you can easily get a signal or reward from the environment. But for language agents, things might be more open-ended, and it can be hard to verify. And as a result, doing search can also be more challenging. You probably always want to have something like a value function to guide a search. But for action space, for conventional agents, the action space is typically very limited. You may only have a very small set of actions, and also sometimes it might focus on maybe something like continuous actions in a continuous space. But for language agents, the action space is much more semantic rich. So basically, you can do anything that you can describe in natural language. And also, these actions are typically discrete. Like in the previous examples we have seen for both the knowledge base and also for web agents, they are both discrete. But regarding policy, it's either rule-based or gradient-based, or maybe parametric, we can call that. While for language agents, it's kind of like new paradigm, allows you to do language condition policy. So this is very different. And also for learning part, for rule-based method, there's just no learning, right? Because human experts just craft everything. But for RL agents, it's typically parametric. And you learn the policy, or maybe you need to learn the value function. Or for language agents, we can do both parametric and non-parametric. So for parametric, you can also do RL. Maybe you can also do like fine-tuning, supervised fine-tuning. But for non-parametric, it's kind of like new paradigm, like kind of like just vision for the stage 3 agent, which you can actually organize external memory using natural language concepts to serve as a new form of continuous training or continuous learning. Yeah, but as I mentioned, it's still kind of like very preliminary, and some of the descriptions in my talk might look a bit hand wavy. And I think this is actually a good thing, because one aspect for that is that it means there's still a lot of like things we need to figure out how to achieve in the future. And current work is just definitely not sufficient. So I want to conclude my talk with a famous quote from the genius philosopher Wittgenstein. The limits of my language means the limits of my world. And I think this is kind of like the core spirit of language agents. Like actually using language as a medium for a lot of like intelligent behaviors that previously we cannot do without language. Okay, so I think that's all about my talk. I kind of like, it's a bit over time, but yeah, just I'm glad to take any questions and to engage in like more discussions with you.
Yeah, thanks for the wonderful talk. Let's see if there are some questions from the audience.
Yeah, I do have some question. First, it's a very interesting talk. I mean, especially for some psychological experiment you showed, it's really captured the eye here. Yeah, so let me see which slide it is into. So it's specifically, I think it's your slide 31, have some question here. So you
31.
did the comparison with different planning strategies.
I mean this one?
Yes, right, yeah. So prior to these slides, you mentioned the knowledge-based Q&A. Maybe since it is related, different kind of knowledge base, they may link with a different planning strategy. So from the one you display here, since you displayed the graph knowledge base before, is there any specific reason you prefer the graph knowledge base versus an other knowledge base design? And also, like for your KBQA, that design, is it just similar to the graph reg?
So by like other types of knowledge bases, do you have like any more specific examples? So I don't
Yeah.
actually have to be honest, we don't actually have a very specific reason to choose a graph structure. It's just that knowledge graph is kind of like most common thing, right? It's kind of more readily available with a lot of like facts in it and with good diversity. And probably you cannot find like knowledge base of other format that can meet the same requirement of diversity and complexity. Yeah.
Then maybe let me clarify a little bit. So for this knowledge base, are you mean the external knowledge base plug in into the language model, more like a external like an article or some Wikipedia, more like the external knowledge you try to plug in to this language model, and before you plug in, this language model may didn't have those domain specific knowledge here. Is that what your design of your knowledge being stored in this KB?
Yeah, I guess I may need to kind of like explain the setup of knowledge base question answering to you. So the task of knowledge base question answering is just, so the knowledge base is given.
Oh,
You
okay.
have knowledge base there, right? And the knowledge base can be very huge. For example, it can has like billions of ages or trillions of ages. And the task of knowledge base question answering is that you are given a question in natural language, and the language model should know how to navigate the KB to answer the question. For example, like in this example,
I
this
see. So it's not a
it's
knowledge base built by you, but it's more like a
yeah,
pre-existing
right.
graph
It's a
knowledge
given.
base.
It's a given one. It's an external environment. Yeah,
I see. And
yeah.
then it's more like in the previous time when they try to find the answer from this graph knowledge base, they utilize a different way, and you found for your design way of searching by the model can find a more accurate answer in this graph database.
Yeah, right. So the most important thing I want to mention was because for a database or maybe for a knowledge base,
Yeah.
doing over it is very simple. There are two reasons for that. First, you have like very mature query engines to do that, right? For example, for database, for SQL database, you have maybe MySQL or something like that, or Oracle maybe. But for knowledge graph or for graph database, you also have Neo4j or maybe Virtuoso. That all these kind of like mature engines for you to query it efficiently. And also, second thing is that because all actions in KBQA, they're just querying actions. As a result, it's not changing the environment, right?
Mm-hmm.
So in this way,
Mhm.
sorry, go
Oh,
ahead.
sorry to interrupt here. Then I'm wondering, since for the language model, it's even with like 2 million token context window, just to understand everything we just fit
Okay.
in the prompt is already a challenging thing. Why in your experiment design, you choose this pre-existed knowledge database as the benchmark to test some of your hypothesis here?
Sorry, could you kind of like elaborate a bit? So what do you
Uh-huh.
mean by like the larger model already has a very support for very long context, and what's
Mm-hmm. So more like I'm constant meeting the issue if I just submit a SOP or a document into a language model and he cannot find an answer. So it's more like the common problem I meet.
okay, yeah. You mean
Yeah.
you can just do text-based QA. You can just maybe feed maybe even a book to the language model.
Yeah, it's
Okay,
already quite a challenging thing. So I try to plug in the benchmark or your experiment to
okay.
link this search with the graph database here. Try to see why you go with that test benchmark and how can plug in your like uh improve the planning with your proposed model-based planning design here and see how it can be leveraged more like combined with some common issue we are facing. Yeah.
So I think one thing I want to make clear is that
Yeah.
uh, I don't really care about the KBQA task itself, like the QA setting or like the formulation, like what kind of specific task it solves. The
Yeah.
reason I use KBQA as a test bed is that, as I mentioned before, in this slide, is actually because it represents a level 4 task, right? Involves grounding to an external environment, and also it requires online planning, which means you need to actively interact with the environment, right? It's really hard for you to find the environment or find a task that satisfy these two requirements.
I see. That's why you pick this as
Yeah.
test bed. Mhm.
Okay, cool. Thanks for the question. Yeah.
Sorry, one more question here. Then, go back to the slide 13 first here. Then do you think your proposed method will be scalable to more general problems, to improve the planning? So you mentioned, like React. Actually, since React is also similar, the reasoning and the action similar to your method you described before. It's kind of like a LM as a judge or as a language model works good as a I think you mentioned the keywords. It's more like compare with generative task, but discriminative task, yeah, works well. So I data sensing, the discriminative task versus this React framework, since the reasoning action is more like with a in the layer in between. They serve as an LM judge here.
Yeah. So what's the question?
So I'm wondering, for the one you present for this discriminative task, you utilize language model to do. What's the difference between this React framework? So I feel similar here.
So for discriminative tasks,
Mm.
the language model is asked to output a score or maybe a ranking. The input is going to be the goal, the natural language specified goal or question, plus the candidate action, right? That's the input. So it takes both the input question and also the candidate action as input, and the outputs a score or ranking. That's called like discriminative. Well, for React, it basically just a generating method. It only takes a goal as input and it outputs an action. It's just like the action is conditioned on the rationale, which is also generated by itself. Yeah. So
Okay, yeah, since kind of heard some like multi-agent design, it's more like a coding. When they have coding error, then send for LM to do self-reflection here. But I get this part, yeah. Then maybe could you elaborate a little bit more how this model-based planning, how you gonna build this model or design this? More like React is easy to understand, and I think for the tree search with real interaction, uh, yeah, it's this more like for the Mr. B here, tree search with real interaction, just adding a reward model in between to decide which branch they should search next.
yeah, that's a good point. For both model-based planning and also tree search with real interactions, you need a score function to inform the agent whether the current state is good one, right? So you can call it a value function or something. Probably maybe some people also call it a reward model, process reward model, but yeah, many people don't like that. And this is why I actually mentioned at the end of the last slide of my my talk that for tasks like language agents handle, so most of them are kind of like hard to verify.
Yeah.
And that's why we need a good value function or scoring function to guide a search. And yeah, you're definitely right. Like for tree search and also model-based planning, we need to have a reward model. And in terms of concrete implementation, so for the tree search with real interaction, it's actually a method from CMU. It's not our work, but we just well, our work is the model-based planning. But both methods just require like prompting the most advanced LLM GPT-4o to estimate kind of like the promise of a current state. So the rule model is also implemented based on like LLM.
Then, do you think, given the nature of this tree search algorithm, then the backend knowledge base, we should go with this graph knowledge base design versus some other maybe like a, vectorized knowledge base design. So, or this kind of search algorithm, no matter go with what kind of knowledge base should works.
So first of all, this is not for KBQA. This is for the web agent environment. It's for web browsing.
Okay.
For KBQA, the search is much simpler, as I mentioned before.
Mm-hmm. I see. Then for link with this web agent, this is for search and answer just online, how they navigating the website.
Yeah. So
Mm-hmm.
you can imagine, like, if you want to do search over the website with
Yeah.
row interactions, you need to click a lot of different actions. You need to click different buttons on the website, right? And
Right.
some click may not be reversible. For example, if you click confirm a purchase, then you cannot go back to the previous state, right? Because you have already made the purchase. So
Yes.
that's why row interactions is challenging. And that's why we want to do model-based planning. And this is different from the KBQA setting, because for KBQA setting, we don't have this kind of scenario with
Yeah.
Yeah.
Thanks for explaining. I get the point here. But another thing in similar is even though it's for web agent design, but the web agent, all those articles, like they click different link, it's still a graph, like linkage node within those web hyperlink. Yeah. So yeah, I'm just trying to link your idea here with some practical problem I'm kind of facing right now. But yeah, thanks for sharing your thought. Yeah, open and yeah, get some thought to see how we can redesign the knowledge base here. Yeah, thank you. Mhm.
Thanks for the question. Yeah, I think, like, in that sense, like, a lot of like environment can be described as graph, because it basically like transitions
Yeah,
between but sometimes the transition can be stochastic, not deterministic. Then probably it's not a graph. Yeah.
yeah. Since I'm actually working in Amazon, so the problem we are facing just we have so many SOP documents,
Okay.
but they are not, I mean, a graph, or they are not the domain knowledge that external language model will know. So more like how can we link this external knowledge with the language model and let him pick up the right tool here. Yeah, but thanks for sharing your research work. Yeah. Mhm.
If you want to discuss more, feel free to send me an email offline. Yeah.
Mhm.
Yeah.
Yeah,
Thank you.
sure. Yeah, thank you very much.
I'd like to discuss more with you offline. Yeah.
Yeah, thank you.
Yeah, great question, great discussion. Maybe one question I want to ask is about the world model. To be honest, I haven't read your paper yet, but I just feel so if you just use say like GPT-4 or something as a world model, it's not perfect. So there will be problems. How do you handle those problems?
You mean the more model is not accurate?
Yeah.
So currently we do not have any specific design to deal with that. It's just kind of like as a very preliminary proof of concept work. And actually, I didn't put the detailed experiment results here. So I actually have an interesting finding that when you increase the steps of simulation, we actually find that the performance drops significantly when we roll it out for 3 steps, because the inaccuracy of simulation. And the best results can be achieved when only simulating it for 1 or 2 steps.
Okay,
When
yeah,
we
that makes sense, right? That because the world model is not perfect, so the more steps, the worse performance.
Yeah, right.
Expected, right? Expected,
Yeah.
basically.
Yeah, and also I think one thing, but not the kind of like a very dedicated solution, but just kind of like heuristic solution, is that when we ask in the model to make predictions, we focus on predicting the core change, the high level core change of the next information in the next page, instead of like asking the model to like generate an actual page, maybe it's HTML or a screenshot. In that sense, the hallucination will be even more serious, right? Because the model might need to predict a lot of like irrelevant details. So in a sense, this is kind of something to relieve the issue you mentioned. But yeah, still, this is a very early effort. As I mentioned, this is a very challenging task to do word modeling for the internet or for the websites. And I just want to show that it's actually promising to use a machine learning model to predict the outcome, and it can actually be helpful. But yeah, definitely in the future, there are still a lot of like important problems to handle, which has not been addressed in this work.
Okay, okay. Yeah, I also see you mentioned procedure knowledge. I just wondering what kind of the state of art of this procedure knowledge, especially how much this is related to, say, language model reasoning. Are there some good benchmarks, good data set, those kind of things for the procedure knowledge?
The procedural knowledge is actually,
Is it
you
just a
can
concept or?
actually look at some. So the format is very simple. So this is a work from Graham Newbeck's group, and they also target the web environment, the web agent environment. And for the procedural knowledge, simply just a textual summarization for a common pattern, which will be put.
For example, it's like cooking. We have several steps and
Yeah, right. It's
summarize
like
this way,
common
right?
pattern. Yeah. Yeah, it still relies on some annotation for the like the final result. No annotation. Yeah, just by interacting with the environment. For example, on the website, it might identify some common operations. For example, like if you want to, say if you want to book a flight, then you probably need to do several steps, right? You need to specify the destination. You need to specify like the leave date and something like that, right? Just
Yeah.
summarize.
I wonder if there may be some, say, a benchmark or database of all these procedure knowledge. So maybe it's kind of related to the chain of thought. So if there are some good procedure knowledge somewhere, so we may query those procedure knowledge and use them as a template of something, or a chain of thought. So maybe we can use those to help solve some reasoning problem. If that makes sense or not? I'm not quite sure. I'm just thinking out of my head.
You mean using existing procedure knowledge to benefit planning for this kind of like web
Maybe
agents?
I don't know yet. Maybe you know more about that.
This is a very smart idea, and yeah, actually some going on work doing this, and also yeah, so basically people are trying to mine the patterns from websites like WikiHow, and
Okay.
also trying to like find some common patterns from maybe a documentation of a website. Yeah, so this is a kind of like something people have already trying to do. Yes, very relevant. Yes, that's a very insightful question.
Okay. Yeah. Thank you. Yeah. One more question is, I think that's probably related to your last slide about the language, the I think the capacity of the language, right? Yeah. Maybe that's one example I want to say is say how about swimming?
Okay.
We want to learn swimming. Can we just learn swimming by reading books and watching videos? Books is about text, about language, and video is about multimodality. But usually we need to practice, we need to interact with the environment. So by that way we can learn swimming. So
Yeah.
my point is language is not enough. What do
Yeah,
you say?
definitely. Yeah. I think this is a very interesting question, and I actually have been thinking about this for a while. So first of all, I never claim that language is intelligence or language is all we need for intelligence,
Okay.
right? I never said that. So there are definitely a lot of things involving like more tacit knowledge that cannot be verbalized. For example, like the example you mentioned, like learn how to swim, right? How to ride a bicycle, things like that. And also there are many evidence that people also have like other types of intelligence other than things like that does not involve language or totally independent of language. For example, like the spatial intelligence, something like Professor Fei Li has been advocated for a while, right? And also like infants who cannot speak, they can also do reasoning and thinking and do a lot of like different types of complex problem solving. But the thing is that I think one critical nature about language is that it's we actually had some discussion before this meeting for some context for other people. So language is actually a projection of like human knowledge. So with language, we can actually with the like massive like web corpus or web corpora, we can actually use them as a shortcut to learn the concept behind the language. So there are many like existing evidence, like the Platonical hypothesis, Platonical cave hypothesis paper, and also some kind of like literature in the linguistic field or maybe in philosophy. There's a term called the conceptual role. So which means the meaning of symbols are not determined based on the reference to external world. Instead, the meaning of signals are determined based on its use within the symbol system. And all this evidence and kind of like provide the like theoretical foundation for why we can just learn through the web corpora by doing language modeling. And by doing that, we can somehow like also learn the concept behind the language. So this is something I think very important. But I definitely don't think like we can just use language modeling to achieve general intelligence or to learn everything. At the end of the day, probably we want to do something like goal-oriented learning with like interactions with the world. Because this is how like our human beings learn, right? Like we have a general goal, we want to survive, and we interact with the world. We achieve different goals, different sub goals, and we continually gain new knowledge from environment. So yeah, that's my opinion. Yeah, I think language is a very important like shortcut. Maybe it provides a different path to intelligence compared with humans, and it might work as a maybe an expedient solution to some reasonable level of performance at this point. Yeah, but to be honest, I don't think that's the right way to achieve general intelligence as human beings.
Okay.
Because it's totally different pattern.
Okay. Yeah, maybe one more question is about specialist and versus generalist. So I think your talk is about generalist. Yeah, I'm wondering what's the relationship between those two kinds of agents, and and I think currently, most agents, the most successful agents, I think, especially comparing, say, for example, superhuman performance, for example, AlphaGo. Yeah, I don't think general agents like language model like GPT-4, they can beat AlphaGo in some expected time. Yeah, so yeah, what do you think about say, specialist versus generalist?
Yeah, I think first of all, so by generalist agent, so the term is actually quite vague. So it's probably not something like it's just like general intelligence, but it's probably not something that we just hope the agent can do everything you can imagine, like you mentioned, like maybe to play Go or and meanwhile to do web agent tasks. So in our definitions, generalist agent might be a slightly narrow. So it focus more on like the environment might be given, for example, just web environment or maybe just a physical environment in your house. And within the environment, it can be generalist. That can achieve like any like natural language specific goals in the environment. But it's not like we also hope the agent to also like play maybe Go better than AlphaGo or something. So that's the first thing. And think the second thing regarding the superhuman performance of AlphaGo versus maybe general agents or maybe just large language models in handling different tasks in general. I think one key difference is that for tasks like AlphaGo, you have a easily verifiable function, verifiable goal, right? You can have the correct, the true reward from the environment. And this true reward allows you to more effectively scale up search, not just for inference, but also for scale up search during training to train better policy. But for a lot of like general tasks, or maybe more accurately to call them like open-ended tasks, you don't really have the true rewards. And I think this is a gap. Why, like for tasks like Go, the agent can achieve superhuman performance, but for other tasks, maybe like math or maybe some even more open-ended tasks, it's hard to achieve superhuman performance because you just cannot have the true rewards. And relying on the real models will quickly get to the selling point. So I think that's a key difference. Yeah, but in general, regarding generalist agents, I still want to make sure regarding the definition. I don't really want to mention that the agent that can do anything you can imagine. It's still like a bit narrow in a sense of like generalist agent, but it's more like a generalist agent to fulfill a specific type of task, but with general goals. So while for specialist agent, I mean more about just only focus on a like very specific goal, like playing Go, or maybe just clean the room. So you don't have any other way to specify the goal. So it's more general in that sense, but still not like general intelligence or general in doing anything. Yeah, that's my take on this.
So for the problem, it's not easy to verify or define even the objective function. So it may be also challenging to, let's say, measure the performance in some sense, right? I mean, a follow-up of the last discussion.
Yeah, so for measure the performance, yeah, we rely on human annotation to annotate the goal state.
Okay.
Yeah, but it's not very scalable, right? It's very, very costly to annotate this kind of. For example, on web agent, people typically rely on the function-based evaluation. So function-based evaluation basically means you write a function to determine whether the current web page satisfy the requirement. For example, whether an item is placed in the shopping cart, something like that. You need to handcraft functions to do the evaluation. So it's very costly and it's not very scalable.
Okay.
Yeah, but I think one interesting possibility is that, but it's very open-ended. If language agents actually become a thing and many more people try to work on this field and they provide a lot of data, a lot of different annotations for different environments, then this kind of like broad goals might lead us to maybe next level intelligence. Because now we have maybe a lot of like true rewards, a diverse true rewards specified by different people in different fields. And then in that case, we may utilize them to improve the intelligence of current AI models. But the thing is that still we're quite limited in the availability of such kind of data. So yeah. So that's kind of like something I hope to happen in the future, that more people provide more annotations, more goals for the task.
Okay, yeah, that's great. Yeah, I wonder if there are still questions from the audience about Yulin. Yeah, it's already a long time. I think that's probably that's it. Yeah, thanks a lot for the wonderful talk. And
Thanks. Yeah, thanks for having me today. I'm very excited to talk about all this. Yeah, and very interesting discussion.
Yeah, that's great. Thanks a lot for the talk. Yeah, thank you.
Thanks.
Yeah. Okay.
And also for people who are interested in discussing further with me, just feel free to reach out, send me an email or whatever. Yeah.
I think I will put the video online, and maybe there will be more people coming later. I mean, watching the video.
Yeah,
and
thanks Dr. Lee
by email or something. Yeah.
Yeah, thanks a lot. Yeah.
Thanks a lot for the talk. very, very insightful. Yeah. Thank you.
Thanks.
Yeah.
Okay. Okay, bye.
Yeah, bye.